So, welcome to the special matrices part 2 lecture. So, in the previous lecture, we have defined what a symmetric, skew-symmetric, and orthogonal matrices are, and there are some one or two properties about the eigenvalues and determinant of an orthogonal matrix. And we have seen what a transpose and dagger operator is. If you don't know the dagger operator, just see the previous lecture of a special matrix. The link is in description box. So because I'm going to use here the dagger operation, because the dagger operation. So today we are going to start with the first definition, that is called the Hermitian matrix. Likewise, we have seen in the symmetric matrix, the definition of an Hermitian matrix is given by the A dagger is equal to A. It means that a ijth component is equal to a ji component and its complex transpose. Okay, so that is a basic definition of an Hermitian matrix, where the dagger of a matrix is the matrix in itself, and this is a relation of the matrix, the elements of the matrix. Okay, so let me have a property of the Hermitian matrix. So that is, so first let us construct the matrix, then we will see the properties of that matrix. So I am writing a matrix A, that is, let me write its diagonal elements as A, B, C. This is D, E, F, which we have written in symmetric matrix also, but here this element in symmetric matrix, it was D. Here it is D and its complex conjugate. Here it is E and its complex conjugate. Here it is F and its complex conjugate. And this is basically a 3 cross 3 matrix, and A comma B comma C, these elements, which are the diagonal elements, are real. Why they are real? Because if you do the A transpose and you are saying that this is equal to A, because A11 element is equal to A11 dagger. So this property must be satisfied for Hermitian matrix, and it is satisfied only when the imaginary part is 0. It means that A is a real number. In the same way, B and C are real number. So the principal diagonal element of an Hermitian matrix are always real. So this is principal diagonal element of a Hermitian matrix are always real. See, you should know, by seeing a matrix, you should know whether a matrix belongs to which category, means it is a Hermitian, anti-Hermitian, or that we have studied late earlier. Because in some of the exams they will ask, if you don't know these properties or how to construct a matrix, or the how a Hermitian matrix look like, then you are, I suppose that you are not going to solve the problems. Okay, and here one more property of an Hermitian matrix, which I will show you how it is true. So the second statement is about the eigenvalue. The eigenvalue of a Hermitian matrix are always real. So I'm going to show you and prove you that the eigenvalues of Hermitian matrix is always real. So if you don't, and one more advice for you all, that you should make a proper notes of all these lectures, because they will help you in your examination times revision. So now I'm going to prove these, how the Hermitian matrix, the eigenvalue of these are real. So I have deleted all that things which I have written in the right hand side of this. So the statement is proof of eigenvalue is equal to real, and for this I am doing for Hermitian matrix. Okay, so let us write the eigenvalue equation. The eigenvalue equation is A time x is equal to lambda time x. So A is your matrix, A is an matrix, lambda is your eigenvalue, and X is your eigenvector. And I'm claiming that A is an Hermitian matrix, then A transpose must be equal to A if this is Hermitian matrix. Okay, so I'm using the definition of Hermitian matrix on the the equation of the eigenvalue. So let me take the dagger of this operation. So taking dagger, so Ax times dagger is equal to lambda x times dagger. You know that AB transpose, there is one property that AB transpose of a matrix, AB are two matrices and I am taking the transpose, and this is equal to B transpose A transpose. Okay, in the same way this dagger operations, so it will be X transpose A transpose is equal to lambda transpose and X transpose. See, here I have not flipped the order because lambda is not a matrix, it is a complex number. I don't know whether it is a complex or real, I have to prove it. So I'm saying that lambda is a complex number in general. So transpose represents the transformation, means the dagger represents the transpose and then its complex conjugate. For any scalar, transpose does not means anything. So here lambda dagger is nothing but lambda star, that is the complex conjugate. So this equation can be written as X transpose A transpose, means the dagger operation here, X dagger A dagger is equal to lambda times star X dagger. Okay, now we have came to this equation. Now multiply this equation, let us called A, multiply equation A by X from right side. Okay, in matrix multiplication there are two types of multiplication, one from right side and one from left side. So multiplying from right hand side we will get X transpose A transpose X is equal to lambda star X transpose X. Okay, from the definition of Hermitian matrix, A dagger is equal to A. Sorry, I'm saying that dagger as uh, transpose, but you shouldn't, but it is known to you that it is a complex transpose. Okay, so X trans dagger A X is equal to lambda star X dagger X. See, Ax is equal to lambda x, that is from our the eigenvalue equation. So this can be stated as, here lambda is a constant, it can be taken at outside from X dagger X is equal to lambda star X dagger X. So from this equation you can conclude that lambda is equal to lambda star. In general, we have taken that lambda was a complex number, and here this lambda can be the eigenvalue of this equation. Ax is equal to lambda x, where A is Hermitian, lambda is equal to lambda star. So this equation says that lambda is real, because if you take a complex number, see, if there is a complex number, let us say that is a plus ib, and we are saying that it is equal to a plus ib, the transpose of this equation, that complex transpose of this equation. Okay, so if you solve it, then it will be a plus ib is equal to a minus ib. So this equation can be satisfied if this imaginary part is 0. If this imaginary part is 0, then a is equal to a star, where a is a real number. So from here you can see that the eigenvalues of an Hermitian matrix are always real. Now let us have these all properties about the antisymmetric matrix. As same as here at it is anti-Hermitian matrix. So our second matrix to discuss is today anti-Hermitian matrix. So anti-Hermitian matrix, the definition, we will see first the definition. It is A dagger is equal to minus of A. The elements are given by Aij is equal to negative of A ji star. Okay. So first let us construct an anti-Hermitian matrix. So I'm constructing an anti-Hermitian matrix. For simplicity, let me construct it for 3 cross 3, and I am writing the elements A, B, C, D, E, F. See, this element by definition it should be minus B of a star, minus E star, and minus F star. So this was from the definition. We have seen that an anti-Hermitian matrix should look like this. Now what about A, B, C? In Hermitian matrix it was all zeros. Sorry, not zeros, it was all reals. In anti-Hermitian matrix, let us say what happens. So our first element is, let us say, call it as A11. So let us say it is x plus iy. Okay, the first element of matrix. Then from definition, minus A11 star is equal to minus, and A11 star is x minus iy. So this is minus of x plus of iy. And I am saying that these two are equal from this definition. So if I these two, so this is x plus iy is equal to minus x plus iy. So this iy cancels out. So this is 2x is equal to 0, implies that x is equal to 0. See, the element was A11 was x plus iy, and from here we have concluded that x is equal to iy, so this is minus iy. So ABC can be purely imaginary number, purely imaginary, or it can be zeros, because 0 transpose is 0 and its negative is 0. So this is the condition that the diagonal elements are either all 0 or all real. So let me state it here. The principal diagonal elements of anti-Hermitian matrix is either 0 or purely imaginary. So this was about how we have discussed the diagonal elements of Hermitian matrix and anti-Hermitian matrix. In Hermitian matrix, we have seen that it was all zeros. Sorry, not zeros, it was all reals. And in anti-Hermitian matrix, that are all zeros or purely imaginary numbers. Let me have a statement for eigenvalues of this anti-Hermitian matrix. So eigenvalue of anti-Hermitian matrix will be either 0 or purely imaginary. See, these are the condition, the eigenvalues of the antisymmetric matrix was also this. The eigenvalues of antisymmetric matrix or anti-Hermitian matrix will be either 0 or purely imaginary. So I'm going to prove this statement here in the same manner which I did for Hermitian matrix. So I am doing it here very quickly. So let us have an anti-Hermitian matrix. This means A dagger is minus of A. Let me write the characteristic equation, that is Ax is equal to lambda x. Again doing the same thing, taking the transpose. So it will be A transpose is equal to lambda star x transpose. Then multiplying the x from the right side, multiplying x from right, we will get x dagger A dagger x is equal to lambda star x dagger x. A transpose is negative of A, so this is minus x dagger Ax is equal to lambda star x dagger x. from characteristic, sorry, the eigenvalue equation says that ax is equal to lambda x, so you can write that lambda x dagger x is equal to lambda star x dagger x. So from this equation, from here we can conclude that minus lambda is equal to lambda star. Okay, let us say that lambda is equal to a plus ib, then minus of a plus ib is equal to a minus ib. This is this and this is this. So minus of a minus ib is equal to a minus ib. So this cancel, it means a is equal to 0. It implies that lambda is equal to plus of ib, that is purely imaginary, or this equation can be satisfied when lambda is equal to 0 plus I0, that is 0, because its transpose is equal to 0. So the eigenvalues that are represented by lambda is equal to 0 or this purely imaginary. So we have discussed this. See, these properties are very important because when in multiple choice question, suppose you identify that the given matrix is your Hermitian or anti-Hermitian matrix, then by seeing the option you can say that suppose there is a symmetric, there is a Hermitian matrix given in the problem and the eigenvalues in 4 options. In 3 options the eigenvalues are given to be complex number, and you know that Hermitian matrix cannot have an imaginary eigenvalue, and there is in only one option that is given to be the real eigenvalue. So without solving you can just claim that that must be the solution. So why there the important you there you will realize the importance of these uh, questions or these properties. So let us more talk about the Hermitian and anti-Hermitian matrix before going to your unitary matrix. So I am having a question. What happens if I multiply a matrix by a scalar? Let's say that a scalar is k or whatever you want to write it. I am writing it as k. So what happens to a matrix? And suppose that matrix is Hermitian. So if you multiply a scalar k by an Hermitian, then what will happen? See, now it depends upon what is k. K is a real number, or it is an imaginary number, purely imaginary number, or it is a complex number. So first you should think about it, and I am going to start. So first, if k is a real number, okay, and I will give you the proofs also how this is happening. So if you multiply by k and let us write the Hermitian matrix as H, then if you multiply it by a k, then Hermitian it will be k times H, and this matrix is still a Hermitian matrix. Hermitian matrix. So if you multiply a Hermitian matrix by a real number, which is a constant number, then the matrix identity is not going to be changed. That remains Hermitian. See how? If if H is a Hermitian matrix, that H dagger is equal to H. If you multiply K times H, then take its dagger. It is equal to K dagger H dagger. And I am saying that K is real, then K transpose or K dagger is going to be the number itself. This is K times H dagger, and H is Hermitian, so it is K times H. See, this dagger is equal to that. Let me write KH and another matrix B. So from here you have seen that B dagger is equal to B. That is a condition for Hermitian matrices. So if K is real, nothing is going to be changed. Your Hermitian matrix will remain to be Hermitian. Now let us see the second case. What happens if k is your purely imaginary number? Okay, so if k is your purely imaginary number and H is your Hermitian matrix, your H dagger is equal to H. See, k H dagger is equal to K dagger, H dagger. H is your Hermitian, so it becomes K dagger H. See, K is your purely imaginary number, then K dagger is equal to minus of K transpose, and transpose of a number is nothing but minus of K. So this is minus of K H. Again, if I am saying that is a matrix C, then this is C. So C dagger is equal to minus of C. So this condition reminds you for anti-Hermitian matrix. This is anti-Hermitian matrix. So there is an important conclusion here. If you multiply a Hermitian matrix by a real number, it will remains a Hermitian matrix. If you multiply an Hermitian matrix by a purely imaginary number, then the identity of matrix is going to be changed. The Hermitian matrix is changed to anti-Hermitian matrix, and you will see this. This is a very important property when you will study the quantum mechanics, where the time evolution operator is given by e raised to power iota ht by h cut. So that H is an Hermitian matrix, minus I, that becomes anti-Hermitian. That very beautifully, the time evolution operator is always a unitary operator. So I'm not going to in that detail because you all have not studied about the quantum mechanics that well. So I'm continuing here. The third one is if K is your complex number and it is not purely not imaginary. Let us say it is A plus IB having both real and constant numbers. So now if I multiply K times H, then KH dagger is equal to A. Let me write in that way. So it was K dagger H dagger. So H is your Hermitian matrix. So it is K dagger H. K dagger is your A minus IB times H. See, it was A plus IB times H whole dagger is equal to A minus IB times H. So we have not seen this type of this types of equations. So from here we can conclude that KH is neither Hermitian nor anti-Hermitian. So it will completely change its identity. It will be a not Hermitian matrix. It will be not anti-Hermitian matrix. It may be any other matrix or any general matrix. It is not any special matrix. Okay, so if you multiply KH by a purely complex number, then the identity is completely changed. It is neither Hermitian nor anti-Hermitian. So on these type of Hermitian and anti-Hermitian properties, let me discuss one question that was asked in Tifr 2014. And the question was the product of Mn of two Hermitian matrices M and N is anti-Hermitian then. And the options are A, that is given are M comma N is equal to 0. Second option is M comma N is equal to 0. Third option is M dagger is equal to N. And the fourth option is M transpose is equal to N inverse. See, I also wanted to look to say what is these operations are, these curly brackets and these square brackets, what does that mean? So I have selected this question in such a manner that you can understand these also. So let us first solve this equation and then we will discuss what this curly bracket and what this square bracket means. See, let us solve it by how it is given. The product of Mn, that is two Hermitian matrix, M and N is anti-Hermitian. So M and N are Hermitian matrix, then M dagger is equal to M and N dagger is equal to N. That is given by our statement that given in the questions. Now it is saying then the product of two Hermitian matrices, that the product of Mn, its dagger is equal to minus of Mn, because it is given the product is anti-Hermitian. Okay, so let us solve this part. So this is equal to n dagger m dagger. So this is equal to n dagger is equal to n, this is m. So this equation look like n times m is equal to minus m times n. So this is equal to nm plus mn is equal to 0. Okay, and this relation is defined as m times n is equal to 0. These curly brackets are called anti-commutator brackets, and this square bracket is called as commutator brackets. And let me have the definition of these operators. Look, these operators, these are called operators. So if there is a operators and written a comma b, it means that it is a times b minus of b times a. See, if a and b are matrices, then you know the product of two matrices don't commute. AB is always not equal to BA. So it is definitely, in general, this is not equal to 0, and I am saying that A and B are any operators. Here the operators are matrices. It may be in quantum mechanics, that may be your position and your time position and momentum operator. So it is in general. So this bracket which I have used here, it is called, this is called commutator bracket. Commutator. This is called commutator bracket, and this is called anti-commutator bracket. Anti-commutator bracket. So anti-commutator bracket is defined as a comma b, that is equal to ab plus ba. So these are very two important definitions of operators, what are commutator and anti-commutator and anti-commutator brackets. You are going to use again and again in many of the problems. So that is why to define these types of operators, I have chosen these problems very well. So the correct option of this is mn is equal to 0, and this I can solve only using the definitions of the matrices. So it is very important to know all these definitions. So this was all about this lecture, and in the next lecture we will be studying the inner product of two versus normalization condition, orthogonality conditions. And we have still not studied the orthogonal matrices and unitary matrices and then properties. So in the next lecture I will be covering the unitary and orthogonal matrices in detail and their properties also. So if you have not subscribed the channel, please subscribe the channel for the updates. Your queries are welcomes, have mail, have doubts, discussion, everything. I will be very happy. So all the best, solve problems as much as possible. Good luck.